Okay, good morning. Week 13. Okay, just to remind or announce, not a reminder, it's announcement that term test 2 can be collected in ETV 216 today, which is April 6th, after 12 p.m. Okay, so you collect your term test. Then if I will post the marking scheme online. If you have any questions on marking, contact the TA and the TA will come to you. Why it was so late? Initially, I thought the TA should distribute out to you. A lot of them don't have the time. Your TA were busy. So I say, okay, let's let you guys collect in my office. And if any question, you contact the TA. Okay. So the agenda today, we are going to look into maximum distortion energy example, which we did not do on Monday. Then I decided to change the topic. The last topic I'm going to cover is buckling. Okay. Well, why I changed the topic is because I met one of your seniors who is doing 3E now, and they are doing buckling, or they were doing buckling and they have not a clue what is going on. Okay. So rather, I was planning to do statically indeterminate structure due to bending. I realized, okay, let's switch to buckling, which we will use for 3E05, which I hope will be more useful. Okay, that's why I changed the topic. So example number 1, which we started analyzing last week, is we have a shaft diameter of 1.5 inch, and it has a tensile yield strength of 42 KSI. Okay. So we're going to use the maximum, for this problem, okay, I'm going to emphasize on using the maximum distortion energy criteria to determine the value of torque, for which yield occurs when P is equal to 16 kilopound inch or kilopounds of force. Okay. So where we stop on Monday is we already sketch out the element. Okay, we already sketch out the element following the transformation. We realize there's a stress Y compression. Okay, and we also have shearing stress, and our shearing stress you can call it shear. It's shear XY and shear YX. Okay. What we are aware of is stress X and stress Z is going to be equal to 0. Okay. So let's look at the maximum distortion energy criteria. Okay. So objective over here is we're going to find the torque. Okay. The objective is to determine the torque. So we are going to apply maximum distortion energy. Okay. And in other words, this is known as von Mises. Okay. Von Mises criteria. So if you think about von Mises criteria, we have a relationship where we have, just quickly to recap, where we have stress A squared, right, minus stress A, stress B, plus by stress B squared must be less than stress U squared. And this is over here, this is a material mechanical property. Okay. And over here, this is based on stress analysis. Okay. So when I say stress analysis, this is what we have to calculate or determine. Okay. So we know that stress A and stress B are the principal stresses. in 3D mole circle. So we have to check, okay, so the first thing, okay, I'm going to teach you the normal procedure, okay? So we have to check that stress A and stress B are the maximum and minimum stresses. We have to check. We have to be sure. Okay. So this can be done through a sketch. Okay. So we're going to sketch 3D mole circle, just a sketch. Okay. So we're going to sketch our 3D mole circle. So we know. Okay. So we know that this is our normal stress. This is our shearing. Come on, you did. Then we have our shearing stress. So we have our normal. Now shearing, clockwise rotation, anti-clockwise rotation. And we know over here is our stress, over here is our stress Z. We know that. Okay. Stress X line is over here. Okay. And I'm going to sketch our stress Y line. Again, these are just arbitrary addition, okay? And then we are going to have a shear. Have another shear. So if you look at, so this is our point X, point Y, and this is our point Z, right? So we know that point Y is over here because the element will rotate clockwise due to the shear. This is our point X. We draw a line. Okay. And then from here, we can construct our circle. So this is our mole circle, okay? And then if we were to construct the other two circles, and pardon me, let me get rid of Z. I don't want Z to be, Eugene, seriously. Let me put Z out here. And now construct mole circle again. Okay. So knowing that point Z is here, we are aware that one of the circle is here, right? And then we are aware that the other circle is over here. Okay. So our in plane, this is our XY plane, which belongs to our in plane, right? And then the next one that we drew, this is your XZ plane, and this is your out of plane. And then finally, you have your YZ plane. This is your out plane. Okay. So we know the in plane, which is your stress A and stress B, are on your in plane, XY plane, in plane. Now, normally, you don't need to draw the 3D Mohs circle. I'm doing it just to check, okay, that the in-plane circle will have the sigma A and sigma B values. Okay, but already we know, even without constructing Mohs circle, right? Even constructing Mohs circle, we know, right? If you don't know, you just sketch Mohs circle. As I said, this is just a sketch. Okay. In the exam, you can just sketch this. You don't need to draw this perfect. Okay. So from here, why the sketch? Because when you sketch 3D Mohs circle, okay, when you sketch 3D Mohs circle, will help to determine that stress A and stress B are not equal to 0, and the in-plane stresses, or the in-plane principal stress, are the stress max and stress min. Okay. Okay. So that is why this is important. Okay. So the first thing that we do, right? So I know now this is a lot to absorb for now. Okay. We have the criteria, we draw 3D Mohs circle, then now we are going to do stress analysis. So from the question, okay, I'll paste this question. Right? And then I'm also going to get the element. Really work. Yeah, it works now. Right? So by looking at the element, we can calculate stress Y. And stress Y is just due to what? Axial loading. Okay? This is just due to axial loading. Okay, before I construct stress Y, things like that. So what we are trying to determine now, okay, we are trying to determine what is stress A and stress B. Okay, what are stress A and stress B? Then later on, by knowing our stress A and stress B, then we can equate this to square our material U stress to determine the diameter of the shaft. Okay, that's the objective. So first, we want to find stress Y. Okay, and if you look at how the structure is loaded, stress Y is just purely due to axial load. There's no bending moment or whatsoever. Okay, and it's going to be compression. So stress Y is equal to minus, so it's equal to Py divided by area. So Py is equal to minus, because it's in compression, I put a minus sign, divided by pi. And we are given that the diameter is 1.5. Okay, change to radius.